We now start the second module of third chapter. We have already introduced linear transformation between vector spaces in the previous module, and here we will show that if we fix bases for the vector spaces, then a linear transformation can be represented by a matrix. This is what is called the matrix representation of a linear transformation with respect to bases. We first start with the definition of an ordered basis. Let V be a finite dimensional vector space over a field F. An ordered basis for V is a finite sequence of linearly independent vectors in V that generates V. So let us understand this with the help of this example. Let V be the vector space F2, where F is a field. Then look at the sets B1 and B2. B1 is the set containing the vectors 1, 0 and 0, 1, and B2 is the set containing the vectors 0, 1 and 1, 0. Now as two sets they are the same, of course, because the vectors are the same. So these are indeed the same bases for the vector space F2, but as ordered bases they are different because of the different sequencing of the vectors 1, 0 and 0, 1. And when we consider the vector space Fn over a field F, then E1, E2, En, where E1 means the n tuple where the first entry is 1 and the rest are 0 and so on. Ei denotes the n tuple where the ith entry is 1 and rest all 0. Then the basis E1, E2, En of Fn is called the standard basis with this particular ordering. Let B given by V1, V2, Vn be an ordered basis for a finite dimensional vector space V over the field F. Now given any vector x in V, we know that it can be expressed as a unique linear combination of V1, V2, Vn, and it would look like x is equal to a1 v1 plus a2 v2 dot 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 an v vn, where a1, a2, an are scalars. Now the n tuple a1, a2, an in Fn, we often denote it by this box x suffix b, and that is called the coordinate vector of x relative to the ordered basis B. Here the positioning of the scalar would surely depend on the ordering of the basis vectors, and that is the reason why we need to consider an ordered basis whenever we want to talk about the coordinates or the matrix, which we will introduce soon. Let us look at one more example. Let V denote M2R, that is the collection of all 2 cross 2 matrices with real entries. Then an ordered basis for V is given by the set B, where these are the matrix units. There are 4 matrix units because it is a collection of all 2 cross 2 matrices, and if we take this particular ordered basis, then any x which is a 2 cross 2 matrix ABCD, typically this can be written as the linear combination of those matrix units, and therefore the coordinate vector for the matrix ABCD would be the 4th tuple A, B, C, D with respect to this particular choice of ordered basis for V. Suppose that V and W are 2 finite dimensional vector spaces over F, and T a linear transformation from V to W. Let us fix two ordered bases for the vector spaces V and W and name them as B1 and B2. So, B1 is the set of vectors V1 to Vn and B2 is the set of vectors W1 to Wm. Since T is a linear transformation from V to W, each of T Vj being a vector in W can be expressed as a unique linear combination of the basis vectors W1 to Wm. And that is what you see, that T of Vj is equal to summation I is equal to 1 to m Aij Wi, where Aij's are unique scalars in the field F. It is clear that the purpose behind this double indexing is that we have the vectors Vj's and the vectors Wi's, and we want to write each of T Vj as a linear combination of the Wi's. That is why we use this double indexing for the scalars and write them as Aij's. Therefore, we have m into n many of them. This gives rise to the matrix A written as Aij, and that is what is called the matrix representation of T with respect to the ordered bases B1 and B2. And this we write as A is equal to box T with the suffix B1 and the superscript B2. So, this is to denote that this matrix representation is for the linear transformation T, which is between the vector spaces V and W, where B1 is an ordered basis for the vector space V and B2 is an ordered basis for the vector space W. And notationally, if V happens to be the same as W and B1 is equal to B2, suppose we name it as B, then this matrix is usually written as box T with the suffix B. So, at this point of time, it would be natural to ask, is it so that if the linear transformation is fixed but the choice of ordered bases are different, then it would give rise to different matrices? And how are these matrices related? Let us first understand the definition well through these examples. Suppose that T theta denotes the rotation operator on R2 given by T theta of xy is equal to x cosine theta minus y sin theta comma x sin theta plus y cosine theta. Then the matrix representation for the linear operator T theta with respect to the standard basis for R2, which is E1 E2, would be this matrix with the first row cosine theta minus sin theta, the second row sin theta cosine theta. Well, how does one get this matrix? If we look at T theta of E1, which is T theta of 1 0, then it is precisely cosine theta sin theta, this vector, and T theta of E2, which is T theta of 0 1, that would be minus sin theta comma cosine theta. So, if you look at the matrix carefully, then the first column is precisely the coordinates for T theta of E1, and the second column comes from the coordinates of T theta of E2. Let us go to the next example. Look at the projection map T from R2 to R2 given by T of xy equal to x comma 0. So, this is again the projection onto the x axis, and with the choice of the standard basis for R2, the matrix representation for T would be the matrix with the first row 1 0 and the second row 0 0. Again, it is easy to understand because the first column 1 0 would be T of E1 and the second column 0 0 would be T of E2. Let us consider the linear transformation T of xy is equal to x comma 0 comma y. The linear transformation is from R2 to R3. We choose the standard basis for R2 and R3, namely B1 and B2. Now, let us calculate the matrix representation for T with respect to this choice of standard basis, and it turns out that the matrix is given by the first row is 1 0, second row 0 0 and the third row is 0 1. Now, suppose we change the basis for the domain vector space R2 and consider this ordered basis B1 dash, which is the set containing the vectors 1 0 and 1 1. Now, with this choice of basis, if we evaluate T of 1 0 and T of 1 1, then it turns out that the matrix representation for T with respect to the choice of basis B1 dash and B2 would be the matrix which you see over there with first row 1 1, second row 0 0 and the third row 0 1. Therefore, with the different choice of basis, we do get different matrix representations. We have introduced the concept of a matrix representation for a linear transformation with respect to a choice of ordered basis. And we have seen that when we have a different choice of ordered basis for the vector spaces, then we do get a different matrix representation for the linear transformation. So, now there are some pertinent questions. Are these two matrices related? And also, what would be the reason behind introducing a matrix representation for a linear transformation? So, we will see that when we try to understand the kernel of a linear transformation, then this matrix representation would help us to translate the problem to that of solving a system of linear equations. Let V and W be vector spaces over a field F. Let LVW denote the collection of all linear transformations from V to W over F. We first see that there is a natural vector space structure for the set LVW itself, and that is given by if T and U are two linear transformations from V to W, then we can define T plus U, and that is defined as T plus U of x is equal to T of x plus U of x, and for a scalar alpha we can define alpha T as alpha T of x is equal to alpha Tx, and it is straightforward that T plus U and alpha T are also linear transformations from V to W. So, The plus is indeed a binary operation here on LVW, and this alpha t in fact defines a scalar multiplication on LVW. So, the observation is that the set LVW is a vector space with respect to the addition and scalar multiplication. If V is equal to W, then we often write LV instead of LVV, which denotes the vector space of all linear operators T from V to V. And if W is the base field F, then the vector space LVF is usually written as V star, and it is called the dual space of the vector space V. Now, this theorem says that if V and W are finite dimensional vector spaces over the field F with ordered bases B1 and B2 respectively, if T and U are linear transformations from V to W, then we have already seen that T plus U and alpha T are also linear transformations from V to W, and therefore with respect to the choice of bases B1 and B2, they would also have matrix representations, and those matrix representations are nothing but, so T plus U, the matrix representation of T plus U with respect to B1 B2 would be the matrix representation of T with respect to B1 B2 plus the matrix representation of U with respect to B1 B2. So, that plus is the matrix addition, and the matrix representation of the linear transformation alpha T with respect to B1 B2 would be alpha times the matrix representation of T with respect to B1 B2 for every scalar alpha. How to prove this statement? So, start with the ordered bases B1 B2, and suppose they are given by the vectors V1 V2 Vn and W1 W2 Wm. We can write T of Vj as the linear combination of the Wi's, the scalars being Aij, and U of Vj as the linear combination of the vectors Wi's, where the scalars are Bij's, and then you can see that T plus U of Vj would be summation Aij plus Bij Wi. So, the scalars that we get would be the pointwise addition of the entries of two matrices. The ijth spot would have Aij plus Bij, and similarly for alpha t of Vj would be alpha T Vj, and that is alpha summation Aij Wi summation over I equal to 1 to n, and therefore if we absorb alpha inside, then alpha Aij's would be the scalars giving rise to the matrix whose ijth entry would be alpha Aij. After addition and scalar multiplication, let us now understand the composition of linear transformations. So, suppose that V1, V2, V3 are vector spaces over a field F, and T from V1 to V2 and U from V2 to V3 be linear maps. Then U composition T from V1 to V3 is also a linear map. That is a routine checking, because U composition T of alpha x plus beta y would be U of T of alpha x plus beta y, and then we use linearity of T followed by linearity of U to show that U composition T is also a linear transformation from V1 to V3. Let us see this example. Consider T from R2 to R2 given by T of xy equal to x0. So, this is the projection operator onto the x axis and u from R2 to R2 given by uxy equal to 0 y, which is the projection operator onto the y axis. If we compose the functions u composition t, then it is clear that u composition t is nothing but the 0 operator on R2. Let us now understand the matrix representation for the composition function. Let V1, V2, V3 be finite dimensional vector spaces over a field F with ordered bases B1, B2, B3 respectively. Let T from V1 to V2 and U from V2 to V3 be F linear maps. Then we know that both U and T have matrix representations with respect to the said choices of bases. Let us write them as box T B1 B2 and then box U B2 B3, and it follows that the matrix representation for the composition map U composition T and with respect to the ordered bases B1 B3 is nothing but the product of the matrices U B2 B3 on the left and then T B1 B2 on the right. Note that the dot on the right hand side of the above expression denotes matrix multiplication. Therefore, here it is very important that the order cannot be changed. U appears on the left and therefore the matrix for U also appears on the left hand side of the multiplication. And the proof of this theorem is straightforward, follows from the definition of the matrix representations. Let us verify this theorem with the help of the example of projection operator. We have already seen the projection operators Txy, which is the projection onto x axis, and Uxy, which is the projection onto y axis. Then U circle T is nothing but the 0 operator on R2. If we choose the standard basis of R2, then the matrices for T and U with respect to the standard basis B of R2 are TB, which is 1 0 0 0, and UB, which is 0 0 0 1. We have already seen that the composition function is the 0 linear transformation, the 0 operator on R2, and here we can verify that the product of these two matrices is also nothing but the 0 matrix. We have seen matrix representations of linear transformations with respect to ordered basis, and we have also seen how the matrix representations of the sum of two transformations or scalar multiple of a transformation and composition of two transformations are related to those of the constituent matrices. We will see how the different matrices with respect to different choice of ordered bases are related. This we will discuss in the next module, and we will introduce the concept of a basis change matrix, and we will be able to prove some very important theorems there.